All right, and we are live. Welcome to Chem 420 Office Hours. We don't have anything on deck right now. We have a completely blank slate. Let's see. So whatever you guys want to talk about, we can totally do that. We have a oh wow. Oh. Ooh, that's a little thin. There we go. Mixtape of the day. Excuse me. Is it's called Don't Die. You can find the link in the description to the Spotify playlist, and that is that's about all I have. I'm still on a little bit of a hip hop kick. This one's got J. Cole, Wu-Tang, and Kendrick. So, you know, it's a good. It's short and sweet. Three songs, 11 minutes, and that's it. So I'm gonna kick it for a little bit. See if anybody joins up. I don't know if anyone will. Um, so if you have any questions, let me know. I'm gonna kind of move through my email, see if there's any fresh business. Oh wow. Again, I'm totally still here. I'm just since I'm the only one here, I'm entering grades. My Gen Chem class just finished turning in a homework set. So I'm punching in who did what. Into the old spreadsheet. What up? What up, Fuzel? How's it going? I'm just chilling. Entering some grades. Hopefully your Monday evening's not going too shabby. I just took a sip of oolong tea, if you're wondering what that satisfied was. Out of a Rick and Morty coffee mug. Because that's how I do. How's lecture going? What are you guys going through? I haven't had a chance to watch the most recent couple. So, Fuzel, you came in a little after. I guess I'd already said this. I don't have any. Nobody submitted any questions through email or Canvas. Oh, cool. What? Not cool that you didn't understand it, but I could possibly help. Oh wow. What was the topic? I'd be totally down to get into it with you if you wanted to. What up? Was it did it involve a functional group? Synthesis. Mechanisms. NMR, perchance? Let's see. Event recordings. I just, Fuzel, I just went to our Canvas site, and it's not playing the today's lecture for me. It said that the recordings have not been fully processed by Zoom meetings, and therefore some recordings made in the same event not yet listed here, blah, blah, blah. So check back for a potentially more complete list, which is lame. So I do not know. Look at Wednesdays. Oh, no worries, Raj. I have absolutely no questions going on right now, so so fire away. See, I'm looking at the end of lecture. Wednesday's Oakham lecture. Looks like we're doing the Swern oxidation, which is pretty cool. Oh, let's see. General question. Great question. Okay, so so in lecture I said that the relationship between resonance structure and geometry doesn't really come in to Gen Chem. You don't really do that that level of analysis. But in OChem, we totally do. So, whoa. Oh, hang on. There we go. Okay. So, for example, with in organic chemistry, you will definitely explore the relationship between different resonance structures and geometry. So, for example, if you look at a carboxylic acid, we have a resonance structure here. Every carboxylic acid has two possible resonance structures. The one on the left is the one that we always draw. But then there's this resonance structure over here on the right. And what you have... Oh, sorry. I'm missing a formal charge. Now, when you look at these two, the one on the left, this is the best resonance structure. Because it has minimal formal charge, right? The one on the right has a positive and a negative, whereas this one is neutral. So it's definitely the best resonance structure. But the one on the right tells us something very important. You can notice that oxygen here has a pi bond. I don't know why I just wrote out the word pi instead of just using the symbol. And because it has a pi bond, we know that it has to be sp2 hybridized, which we haven't talked about in Gen Chem yet. We'll start talking about that on Wednesday. It has to be sp2 hybridized, and it will be trigonal planar bent with a bond angle of 118. And the thing is, because both the true structure of the molecule, remember, is the superposition of both resonance structures. All right? Both resonance structures. And so the true structure of the molecule is a combination of these two. So since there's a resonance structure where that oxygen has a pi bond, that oxygen has the same geometry in both structures, right? Because there's only one molecule. So if you can draw a resonance structure where it has a pi bond, that changes the amount of electron groups around the molecule. It makes it trigonal planar and then bent, and gives it a different bond angle than you would expect if that resonance structure wasn't there. If that resonance structure wasn't there, it would be a bent tetrahedron, and its bond angles would be 105. So that's an example of how resonance structures influence or dictate the geometry of a molecule. Totally. So that's an example of the you do that type of analysis. Over and over in Chem. So that's an example of how resonance structures influence geometries. Yeah, man. So yeah, sorry for the the deadness on this end of the line. But totally no worries. Okay, let's see. Are there different ways to draw a constitution of a compound? Okay, so is let me ask you a question to help me answer your question. I think the answer to your question is yes. If I'm understanding your question. So there's something called let me know if this is what it's about. Constitutional isomers. All right. And constitutional isomers are the definition of constitutional isomers is they are different compounds or possibly different structures with the same chemical formula. All right, different structures with the same chemical formula. So, for example, if you looked at, yeah, totally, constitutional isomers. So for example, the chemical formula C4H8. All right, this chemical formula this is the chemical formula for more than one compound. This is the chemical formula for butane. Whoa. Sorry about that. I just drew a pentane. Right? It has 1, 2, 3, 4 carbons. All right, and 8 hydrogens, 3 on the end, each end. So 6 on the ends, 4 in the middle. But another constitutional isomer, you can get another constitutional isomer, for example, if you draw the chain with 1 fewer carbons, so 1, 2, 3, and then that 4th carbon, take it off the end of the chain and place it in the middle. 4. So these are 2 constitutional isomers, different structures with the same chemical formula. So there are usually, most chemical formulas have more than one constitutional isomer. Now C4H8 is the easiest example. But let's take a look at one that's a little harder. C5H12, for example. So the easiest and first constitutional isomer you always draw out is the straight chain carbon. All right, pentane has 1, 2, 3, 4, 5. All right. So this is a compound. Now to get the constitutional isomer, what you want to do is remove 1 methyl from the end and move it over 1 atom. So you can get a constitutional isomer if you go 1, 2, 3, 4 carbons. And you move that methyl on the end, didn't mean to make it red, over 1. All right. So this is a new constitutional isomer. Again, we have 5 carbons. And then you can try the trick again. Let's move the methyl over 1 more, see if we get a new compound. Turns out we don't, because if we, or actually, to be correct, I should number from this side. If we number this compound 1, 2, 3, 4, you can see that it's not new. 5 is attached to 2 here, just like 5 is attached to 2 here. So it's each a 4-carbon chain with a methyl attached at carbon 2. So this is not new. So this is not a new constitutional isomer. Once you run out of options with a 4-carbon chain, you can bump down to a 3-carbon chain. So here we have 1, 2, 3 carbons. And we could try putting our 2 methyls on this carbon. 4, 5. Here's a new constitutional isomer. So these right here are the 3 constitutional isomers for pentane. For C5, H10. Is that what you're looking for? What if there are more hydrogens and the same amount of carbons? Well, so first off, there's actually an equation for the maximum amount of hydrogens that you can have in a molecule. So if you have N carbons, the maximum number of hydrogens is equal to 2 times N plus 2. All right. So for the example that I gave, oh wait, hang on. Let me look back there for a second. I may have made a mistake. Oh, I did write down here, I wrote C5H10 when it should be C5H12. So this is the maximum number of hydrogens that a carbon chain can hold based on the number of carbons. And the example that I had just done actually had the maximum amount. Because, for example, if you had 5 carbons, then the number of H's you could have would be 2 times 5 plus 2, which is 12. So actually adding more hydrogens on to the previous molecule isn't possible. Yeah, and the answer to your question, they do have to look different, but sometimes it can be deceiving. So, like, for example, sometimes you're trying to find new isomers, and they can look totally different. And it can be hard knowing, like, are these different? Are they the same? So here's how you determine. Here's how you determine whether or not two structures are different. All right. First, the first thing you want to do is find the longest carbon chain. That looks like E chain. And number it. All right, find the longest carbon chain and number it. So if you look at this compound here, we have 1, 2, 3, 4, or maybe we have 1, 2, 3, 4. Okay, turns out that's the same. You could also number it this way: 1, 2, 3, and 4. All right. Then you find the carbon chain in the other compound. Let's see, the longest chain, 1, 2, 3. That doesn't look very long. But if you look at this, it also is 1, 2, 3, 4. You can see that with the green numbering, we have a 4-carbon chain with a methyl, a CH3, on carbon 2. So these are the same. And the best way to identify whether or not they're the same is you find the longest carbon chain, number them, and see if they have the same types of substituents attached. Okay, here, let me see. You've got a flurry of questions. Let's see. Principal quantum, max number of electrons. Yeah, max number of electrons is 2n plus 2. That's not the principal quantum number, though. That n is the number of carbons in your molecule. So for 4 carbons, 2n plus 2 would be 10. 10 would be our max number of hydrogens. Oh, which... Let me see. I may have messed up the chemical formula for my first example. Let me see. Let's see. Oh, no, not there. Oh, I did. I messed it up. This should be... I totally did the structure for C4H10. Because there are 10 hydrogens in both of the molecules that I've drawn. So sorry. Okay, I'm looking. Oh, max number of electrons that hydrogen can have is 2. So that's an introduction to constitutional isomers. I actually think they have you draw some constitutional isomers in lab exercise 5 for Gen Chem, interestingly enough. Totally. Are there any other questions out there? Oh. Who doesn't like a good mic pop? Whoa. What do you know about that? We broke 30 minutes today. That's longer than most office hours. Most Gen Chem office hours go. Sorry. That's not longer than most Gen Chem office hours. Longer than most O-Chem office hours go. Gen Chem office hours are like a short one's an hour. It's usually 1 to 2 horas, which is Spanish for hours. Gotta represent my dad's home country. By saying hours in Spanish, of course. Dude, does it say Chem 400? Did I mess that up again? I could have sworn it says Chem 420. Here, I'm going to investigate. Oh, up at the top. Oh, late. Okay, that's where it says Chem 400. Oh, man. How embarrassing. We're already deep into the live stream. Here, let's fix this. I think I do this roughly once a week. Ooh. Where'd that 0 go? There. Now it's Chem 420 office hours, and there's nothing anyone can do to stop it. That was a good catch, Raj. Dude, Raj, I don't know what I'm gonna do next semester when you're not here in YouTube hanging out with me, you know? Or like this summer, I'm teaching a Chem 305 class this summer, purely online. I think fall semester might be back to in-person instruction. We'll see, but summer's gonna be pure digital for neither Gen Chem or O-Chem for me. It's gonna be a intro chemistry class, which will be something new. I've taught it before, but not since... I haven't taught it at Folsom Lake, and the last time I taught it was summer of 2016. So it's been a minute. Yeah, totally. You know, it'll be fine. Oh, yeah. Yeah, bro. They canceled. They decided not to, and this is district wide, all Los Rios. Decided not to offer any 400 or 401 over the summer because there's a chance that fall might be digital too, and so if someone, heck yeah, the concern was that if someone took Chem 400 digitally over the summer and then 401, if we're forced to go digital in the fall, they could get through a year of Gen Chem without ever having to physically step into a lab. You know what I'm saying? And so that's why they decided to only offer the intro class over the summer. So hopefully, even if fall is still purely digital, they will, at least in the spring, have to take a physical lab. So who knows? Who knows? We'll see where this pandemic goes. But yeah, I would love to see you pop up. I mean, I'm gonna be live streaming lecture 4 times a day because it's summer session, right? So it's gonna be 4 lectures Monday through. Oh man, that's what they want to stay away from. I know. The labs are awesome. And I have to say, like, having taught in several departments, I think that the lab classes set up at FLC by the Folsom Lake College faculty have done a really good job of designing their lab curriculum. I think it's better than any other experiment set that I've seen, with the exception of the calcium chloride. Well, we got that ICP going. Before we got the ICP going, the calcium chloride elemental analysis lab was probably the worst because the probes we had were garbage. But with the atomic, the AA spectroscopy, it actually turned out not too shabby last time I taught the class. Oh, wow. I just saw a slow, lazy fly buzzing on by. And you might have seen him too if I had a webcam set up. If you are, oh, wow. Bouncing all over. If you're joining us a little late, I have no questions right now. We've been talking a little bit about constitutional isomers, a little bit about resonance, but we're down for any questions. I'm down for any questions. How are constituents different than Lewis structures other than not showing the name and electrons? By constituents, do you mean constitutional isomers? So I'm not quite sure if by constituents you meant constitutional isomers or if you meant the skeletal structures I was drawing. So once you let me know, then I can let you know. My guess is you're asking about skeletal structures. Which, if you are, in a Lewis structure, you draw out every bond to every atom and all the lone pairs. And this gets, this gets tiring very quickly. All right, so for example, this is a Lewis structure. With skeletal, it's way faster because you're not drawing any carbon-hydrogen bonds, and you're not writing in carbon at all anymore. So the skeletal structure just looks like this. Note that in a skeletal structure, you still draw bonds between hydrogens and non-carbon atoms. And depending upon how lazy you are or how precise your instructor is requiring you to be, you still draw in the lone pairs. I usually, for the first semester, when I'm teaching first semester OChem, require my students to draw the lone pairs because they need to learn that they're there. And then second semester, I don't care anymore. So I kind of give them a late bedtime when it comes to their lone pairs. Second semester, they don't have to worry about it. But first semester, more precise. Yeah, the only difference, well, you don't draw hydrogens. You may or may not draw the lone pairs. And then carbons, you no longer write in the C. So you can see that if I numbered my carbons in my Lewis structure, 1, 2, 3, they'd be here 1, 2, and 3. Same structure, different ways to depict it. One you can draw much faster. And so, like, I only when I'm teaching OChem, I just tell the class first day, you have to learn how to draw skeletal structures because that's the way I'm going to be doing it. You'll fall behind taking notes if you can't adapt to this way of depicting structures. So anyways, that is the difference between Lewis and skeletal. Are there other questions? Oh, let's see. How come it's always bent like the lines? Oh, great question. Here, let me pull that slide back up. Because in a skeletal structure, by default, a skeletal structure has a carbon at every vertex. All right, that's just by definition, that's the skeletal structure format. If you drew like a straight line, how do you know how many carbons there are? right? There's no real way to tell. Oh, dude, totally not a childish question. It's just the convention. The real reason why they do kind of those like those bent lines. Well, one, it actually does reflect the shape of the molecule. They are kind of zigzag. Carbon chains are zigzagged. If you study their actual structure, so it reflects the structure, but also it creates a user-friendly way of being able to identify how many carbons are in the molecule without explicitly saying it, because you can just draw the backbone and then you're like, oh, 1, 2, 3 vertices, 3 carbons. So so that's why they're bent. Totally. Let's see. Dotted line. Why not the dotted line? Okay. Great question. You're talking about the dotted line from when we with Lewis structures, like 3-dimensional stuff. So like for example, let's look at a Lewis structure for I'm going to put a bromine on here. So here's a Lewis structure for 2-bromopropane. All right. Now when you look at this thing with a skeletal structure, we totally do use the dotted line here for the bromine. Yeah, totally. You totally can use the 3-dimensional structure. The reason why you didn't see it in the previous compound is because the only things that were on wedges or dashes were hydrogens, and we never draw those hydrogens in. So like this thing, for example, if I were to draw the H's, which would make this not skeletal, we totally can, and this is where all the hydrogens are. So this right here is 3-dimensional, not skeletal. Yeah, totally. So the 3-dimensional stuff, the wedges and the dashes that we learned today in lecture, totally come into the skeletal structure. It just not every skeletal structure has non-hydrogen things on wedges or dashes. If it's a hydrogen, we're not going to add that in. It's still there, but we're not going to show it because it's implied. If it's non-hydrogen on a wedge or a dash, as it is here, right, with this bromine, then we include it. So you totally see wedges and dashes in skeletal structures very frequently in organic chemistry. Yep. It is totally ignore the H territory. That is exactly what's going down. Yeah. That is 100% it. Totally. We don't talk about H. We don't think about H. It's part of our past, an important part of our past, but we're moving beyond it now. That is 100%. And hydrogen, meanwhile, is crying itself to sleep every night on a tiny subatomic pillow. Or maybe atomic pillow, I don't know. Oh, let's see. Poor Boar. Oh my gosh, that made me laugh. No, don't cry for Boar. Don't cry for Boar. That dude was a physics baller. He comes up in physical chemistry all the time. Yeah, don't worry. He's not just like playing juvie in Gen Chem. For a community college, maybe, but no, he comes up in PChem all the time. Super foundational, super important human for physics and for chemistry, which is why in PChem, i.e. physical chemistry, you deal with Neil all the time. Oh, I like that. In physical chemistry, you deal with Neil all the time. PChem. Get ready to deal with Neil. Yeah, totally. Don't be sad. Niels. Because it's Niels Bohr. Or is it Nils Bohr? Did I just misspell his name? Let's find out. Oh, no, yeah, I got it right. It's Nil. I think it's pronounced Nils. Nils Bohr. There we go. Get ready to deal with Niels Bohr. Oh, turns out he was Danish. I never knew. Oh my gosh. Heck yeah. Heck yeah. Honestly, the only thing that's holding me back, other than a lack of rhythm, is the concern. Do we really need another white rapper? That makes me a little hesitant. But the truth is that I don't think there are many chemistry rappers out there. I could carve out my my new subgenre of rap, and then there's got to be other chem profs out there who are hip hop enthusiasts, and so then we can throw down and have some epic chemistry rap battles. It'll be pretty stinking rad. And it'll all be thanks to you, Vraj. When I go multi-platinum. I'm gonna thank you. Oh, dude, I could rap lecture. Oh my gosh. Now I want to do this. Like, I want to do this for real. That is so good. Heck yeah. Dude, okay. What? Ya boy Raj. Dude, now we doing it. Wait, where's my... There it is. I needed my rock on emoji. Oh, great question. Um, so the reason why, so I was pre-med, right out of high school. I went to a community college, in Southern California, and I was good at math and I was good at science. So everyone kind of in my life at the time was like, "Oh, if you're good at math and science, you should be a doctor." And so I was like, "All right, that makes sense to me." So I picked pre-med. And Vraj, as you know, um, if you're going pre-med, you have to take OChem, and organic chemistry terrified me because it just has this reputation, right? Like, this is the class that doctors fail. You know, this is it was the boogeyman. It was out to get me, and so because I was so afraid of it, I studied harder than I'd ever studied for anything else in my life. And I realized two things. First, when you study, like, I was studying hard for it, and it's not that it was easy, but it wasn't as bad as I had been led to believe. And then the second thing I realized is I loved it. Like, I loved it. It was awesome. It was so cool that by the end of taking a year, after taking a year of OChem, I no longer cared about being a doctor. All I wanted to do was that. I wanted to do that thing. And so I declared chemistry as my major, and I got involved doing research as an undergrad, went to grad school, and the rest, as they say, is history. It landed me in this current job. So that's why I abandoned pre-med, because OChem was too cool to not do for the rest of my life. So yeah, so that's how I dropped pre-med. Ooh, see, dude, I felt like I was smart in chem, at least in high school. Oh, oh man, totally. The thing, dude, the thing about OChem is it's a lot more conceptual. You know, like Gen Chem is very rigid. Gen Chem is like, it's like you have to cover these topics. Topic A, topic B, topic C, and you move from one thing to another, and some things are kind of connected, but not everything is. It's these discrete little chunks. Whereas OChem, OChem is like everything's connected. The concepts that you learn and discuss in the first semester, not the first semester, in the first week of the first semester of organic chemistry, you will be using those same concepts when you take the final exam for the second semester. Everything grows together. It is, for lack of a better term, very organic. And so there's this part of it where you start learning these things and then applying them, and you add more and add more, and it builds and builds and builds and interconnects and weaves together. And it's beautiful. Whereas Gen Chem, it's like this topic, now this topic, now this topic, now this topic. Some of them are connected, some of them aren't. And it just is what it is. Whereas organic is this beautiful, blossoming flower of science. It defies description. You just have to take it and taste it for yourself. And that's what I think of that. Let's see. Yeah. Yep. Yeah, totally. Totally. Dude. Dude, I totally feel you. It bounces around. It's not very coherent. It's like you're force fed to take bites of all these different flavors. And yeah, totally. Like honestly, I think general chemistry curriculum could do for a significant overhaul, because the things that you use the most, for example, things you use most in OChem from Gen Chem are hybridization and intermolecular forces, polarity and stuff. You cover that at the end of the first semester, but then you take a whole second semester of Gen Chem, and then the stuff that you covered 2 semesters ago now is what's important in the beginning of first semester OChem. I feel you with the frustration with Gen Chem jumping around. I think that as a scientific community, we could do a better job of possibly organizing it. Unfortunately, the way that curricula are set up across the country, everybody kind of does it with the same progression, and there's nothing that can really change because you have to cover the same material more or less as everyone else in the first semester, second semester. So it's really beyond our power to change, unfortunately. We'd have to get the entire country to change with us at the same time. Um, that's a great question. Um, Theoretically, the answer is yes. That being said, I know that the lecture schedules are pretty tight, and to cover the amount of new material, or the amount of material that we need to for each class, in the amount of lectures we have each semester is a pretty significant challenge. So it'd be it'd be hard to squeeze in a an OChem review. Also, it would only be relevant to those people going on, which most people are done with chemistry after Gen Chem 2. That would be super cool. Those are totally um, those are excellent ideas. Um, and I mean, you know what you could always do is like hit me up right as you're finishing up 401, or maybe even better than that, right before you start 420, and you can be like, "Yo, what were the things from Gen Chem that were the ones that I really needed to focus on?" And I can tell you like, "Oh, hybridization, bond polarity, molecular polarity, intermolecular forces." If you can like have those down, you'll be good to go. And I can tell you, I can remind you when that when that comes around. Let's see. Heck yeah. Dude, a student club would be an excellent kind of venue to... Dude, I totally would. I'd totally be down to host like a workshop or discussion group or something in your pre-health alliance club. Totally. Faux show. That would be super fun. Heck yeah. Yeah, man. Absolutely. Let's see. Of the... Cool. Question. Now I have a question. Associated Students, Folsom Lake College. Oh, cool. Um, honestly, um, I'm not really sure. I'm not really sure what the previous director of finance did. Oh, that's rad. Alrighty, I think if totally. Yo, I think if we're out of chemistry questions, I think I'm gonna bounce. I'm totally down to hang out, answer more if there are more. But if not, then think I'm getting to the place where I'm gonna call this stream. Solid. Thanks for and spicing up my my dead Ocam office hours. Alrighty, and again, anybody who's been watching silently, Fuzail, I don't know if you're still there. Thanks for coming, hanging out. I'm here every Monday and Wednesday. You can hit me with your questions live. You can email them in ahead of time, and if you can't attend at this time, we can make sure that we still get your questions answered. Thanks for popping in. I will catch you guys on Wednesday.